to the Code of Chemistry, where we talk about how data, simulation, and machine learning are changing science.
And I'm John. I work with the machine learning models that accelerate chemistry research.
I'm Faye. I use quantum chemistry and density functional theory to model molecular systems.
And I'm Alessandro. I specialize in Monte Carlo methods and statistical modeling of materials.
In this episode, we're talking about a big shift happening in computational chemistry. Researchers are moving beyond traditional tools and using machine learning and smarter sampling methods to make discoveries faster and more efficiently.
Before we dive in, let's define some key terms. First, DFT stands for density functional theory. It's a quantum mechanics method that helps us simulate how electrons behave in molecules and materials. It is the foundation of modern quantum chemistry and materials science. Machine learning is a way for computers to learn patterns from data, so instead of coding everything explicitly, we can train a model on examples. Monte Carlo methods use randomness to explore a system's possibilities and find better outcomes over time. And exploration versus exploitation is a concept we'll come back to. It's the trade-off between trying new things, exploration, and sticking with what works, exploitation. Oh, and GRG. If you've seen it in tools like Excel, it stands for Generalized Reduced Gradient. It's a solver for optimizing systems with many variables.
Alright, now that our audience is armed with the necessary jargon, let's talk computational methods.
Let's start with the classic method, DFT.
DFT is still the workhorse in computational chemistry. It lets us simulate molecular and material properties, things like energy levels, reactivity, or even how a material absorbs light.
The downside is speed. DFT is accurate, but it can be painfully slow, especially if you're running simulations on large systems or hundreds of candidates.
I'm currently using DFT to look at how different compounds, particularly carbodiamides, change under pressure and how those properties change as a result of that.
That's where the bottleneck shows up. Even if DFT gives us gold standard results, it's just not scalable on its own.
So, what do we use when we can't calculate everything from scratch? Monte Carlo.
Monte Carlo methods are all about sampling. Instead of checking every single possible molecular configuration, we make random tweaks to a system, evaluate the result, and decide whether to accept the change. Over many iterations, this helps us find stable, low-energy configurations.
It's like a guided trial and error process, but statistically sound.
For example, I use Monte Carlo simulations to study phase transitions and short-range order in metal alloys. While I could spend all my time doing DFT on every structure the computer could possibly think of, I instead select random structures and modify them until I converge on statistical equilibrium for my particular set of conditions.
And this is where that exploration versus exploitation idea really kicks in. Monte Carlo lets you explore widely early on, then hone in on the most promising areas.
Now, John, you're doing something different, using machine learning to skip a lot of this heavy lifting, right?
Exactly. I work with a model called AIMNet2. It's trained on a massive set of DFT calculations, and once it's trained, it can predict molecular properties in milliseconds instead of hours.
So you're getting DFT-like insights, but way faster?
Right. It's like distilling all that DFT data into a fast, lightweight model. I use it to screen large numbers of molecules quickly, and only run full DFT simulations on the top candidates. For example, I use AIMNet2 to filter through Diels-Alder reactions to find low-energy geometries. This would save computational costs later. When I would want to focus on promising molecular geometry, I would use QChem, which uses DFT methods.
And that becomes the start of what we call adaptive workflows, where your system gets smarter as it goes.
The exciting thing is how these tools are starting to work together. Machine learning, Monte Carlo, and DFT each bring something to the table.
Machine learning gives us scale. Monte Carlo gives us flexibility. DFT gives us depth. And together, they create a pipeline that can adapt and improve with each run.
And that means faster discoveries in material science, drug development, catalysis, you name it.
That's it for this episode of The Code of Chemistry. If you enjoyed this conversation, share it with your lab mates, coworkers, or fellow nerds.
We'll be back next time with more stories and tools from the world of computational science.
Until then, keep exploring the possibilities.